Thank you. It's a pleasure to be here. I'm going to talk about how machine learning can be combined with something like reasoning, kind of reasoning we do. I was first thinking of presenting both analysis and synthesis cases, but then I figured that I'll only focus on synthesis. I hope that makes sense for material sciences. So think of trying to synthesize some materials. I'm talking about something which is like something called model-based reinforcement learning. We have been using in the Curious AI company, and we have been developing this technology, and we have been applying it, for instance, in control of industrial processes. This is an oil refinery in Finland. We haven't actually touched that oil refinery, but we have been demonstrating our stuff with the simulator of that refinery. So now next steps are to actually implement stuff in the actual refinery. The very same technology, which works in such a way that, think of a human. You start working with a machine. You try something out, you see how it works, and then based on that, you can figure out, you can plan, you can reason what you should do in order to get to a particular goal. Timo Roman just gave an excellent presentation about self-driving cars. We have also been working with self-driving machines. In our case, we have been demonstrating automation of mining machines. Again, we have demonstrated in simulations. Now we are implementing it in live real machines just now. But the problem here is that it's very difficult to gather all of those millions of miles and so on. It's a niche application. If you think of how quickly humans can learn, we can do it very quickly. We shouldn't need all of those millions and millions of tons of data to really learn. And the reason why we can do it is because we build a model. As most of you are physicists, right? You understand modeling, you understand dynamics models. If you have a model of the dynamics of the system, how the system works, then you should be able to work your way backwards and figure what to do in order to get to a particular goal. So that's exactly what we've been doing with this particular machine. Currently, Sandvik already has automated some of the machines. It uses very traditional engineering approaches. So you recognize certain situations, and then you have defined what to do in those situations. It's very difficult to cover all possible situations that you could run into, and that's why it's much more flexible to tell that this is the goal, this is where we want to go, and sorry, I have problems with the clicker. So you tell what the goal is, and then you let the system try it out. How does the world work? What if I turn this wheel? How does the world behave? Find a causal model of the world, and then use reasoning, planning to figure out what to do in different situations. It's much more versatile and flexible in that you don't need to cover all new situations. If you run into a new situation, you can figure out what you should do. You might never have done that, but if you have a compact model of the world, you can predict how the world responds and then do it. So this is something called model-based reinforcement learning, and I'm going to talk about why it's so hard. It's been very, very difficult to get deep learning stuff do that. So that's why, for instance, Timo Roman is taking this approach where you've basically you gather a lot of data and you have humans labeling stuff and so on. It's not like the computer is trying to understand the goals and then reason its way backwards. Why is it so difficult? And then I'm going to explain how we can solve that, and then just few slides about maybe how that could be relevant to material science. So, model-based reinforcement learning. First, let's have a look at what is model-free reinforcement learning, because that's what most reinforcement learning in the world is. In model-free reinforcement learning, you are directly learning so-called policy network, or basically the recipe of turning your observations into something that you do. So it's a mapping from state and goals to what you should do. It's very slow to learn, and if you do reinforcement learning, this is not something that you were talking about, but you can do reinforcement learning where you give punishment and rewards to the system, and then it's gradually changing its policy so as to optimize something. It's very fast when you operate, because once you have the policy, it's blazingly quick. Just tick, computation, and you're done. So it's like reflexes. And humans have this mode. But we have another mode, which is largely missing from the toolbox of AI researchers nowadays, and that's model-based reinforcement learning. So in that we also use neural networks to learn something, but this time it's the predictive causal model. We learn to predict what will happen if we do something. So now the actions are actually inputs to the network, right? So you think about, what if I do this and that and that? I wonder what will happen. And then you learn a system, predictive systems, to make a prediction. That's not a black box thing. You know, neural networks are often considered black box things. This is no longer black box because it can explain its reasoning. It can explain what it thinks is happening. Now, when you turn that into actions, you actually have to add planning, because you don't have written sound. What do I have to do? Well, I can use that blue box. I'll have the blue box for the rest of it.
Oh.
Let's just try this one.
Hello, can you hear me? Excellent. So now we just have to add planning to the loop because we don't have the actions already. The actions are the inputs, and now we know the targets where we want to go. We know the goal, but now we need to work our way backwards, find the plan, what to do now. Simple, right? Anybody could do this. Well, I mean, yeah, there are some drawbacks, like simulation can be, doing this planning may be costly and all kinds of funny things, but if you have a good model, this can be really tremendously nice. So here is an example where you control a humanoid robot. This has been done a long time ago. You have a perfect model of the humanoid, and then you have many other things. So if you know what you want to do, you can just work your way backwards and figure out what to do. Perfect. I'm not going to show all of them because of time limitations. My previous company, Zen Robotics, I was actually working there implementing something like that, model-based reinforcement learning with actual real-world robots, which learned to do this. It was next to impossible to program how to manipulate waste. That's actually that's a demo setup. It's very nice, but actual production is messy. All kinds of funny things can be there. And these systems have learned to do that. They have formed a system that can predict what's going to happen, and then they can figure out what to do in order to get the right pieces into the right buckets. So that's something which can work really well. So why doesn't everybody do it? There's a slight problem, which is that it fails almost invariably. You try to do it, you build this funny neural network. Here is an example. So we, on the left-hand side, we have a graph which shows the evolution of the quality of the plan as planning goes on. You start with a good plan, and then you check what's going to happen, and then you work your way backwards with gradient descent and so on. You update the plan. You make it better. Or so you think. The red line is what you think, or what the AI thinks is going to happen. The AI is improving the plan all the time. Whoa, 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 getting better, getting better. The blue line is what actually happens. So it's completely delusional. If you have a perfect model, this won't happen. If you have a perfect model, then the red curve and blue curve will coincide, right? But we have a learned model. We have learned something from data, and this model is not perfect. There's a phenomenon. My clicker doesn't always work. There's a phenomenon known as adversarial examples. If you have a neural network, and on the left there is Panda, and the network has learned to recognize all kinds of things, then you ask the network a question, how should we change this in order to make it a gibbon? And then you work your way backwards, and the result comes out. You have to add this funny little thing, and then it's a gibbon. So on the right-hand side, the network is sure that this is a gibbon, right? Well, no. And this is what happens if you try to apply deep learning for learning the causal model, and then when you work your way backwards, let's find a good way to get to granny. You're not going to get to granny. It's just going to give you rubbish. So the problem we have is that basically this planning process is equivalent to adversarial attack. We are attacking our own model. Neural network inversion is not stable, so I'll skip some. So basically, we have a huge problem, and the root cause is that these neural networks have no idea whether they actually know something or not. Even if you give them something which is outside of their training set, they can completely fail, and they will do that without any warning. They'll just fail. So when you start doing planning, the network will happily find some solutions which are nonsensical, and it's actually just fooling itself. How am I doing with respect to time? I have 6 minutes. Great. So we'll fix that. We'll give the network the ability to understand what it knows. That's necessary to fix this problem. And first, there are many, maybe I can skip. We tried many things that don't work. Many different things have been proposed for giving neural networks the ability to understand the confidence intervals of predictions and so on. But the problem is that when you apply planning, you are actually also doing adversarial attack against those predictions of confidence. So I'll just skip, but most of them fail. The only thing that actually did work was something that we've been working on, denoising autoencoders. They are models which learn to denoise data, and by doing that, they learn the density model of their inputs implicitly. So you train the model with corrupted versions, and then you ask it to produce the original version. So a physicist's explanation would be that the corruption process is like diffusion. You are moving your data points randomly, so it's like diffusion process. And then when you train the network to recover the original, you're learning to go backwards in the the diffusion flow. So then you are actually learning the gradient of the log probability density of your data. Hey, I love being in the audience with physicists. This was the simplest explanation ever. You have no idea how hard it is to explain this to computer scientists. Right, so we have this denoising autoencoders. They learn the gradients directly. And since we have a network which learns the gradients, we don't have to do any backprop or anything through that. We already have the gradient. So it's immune to adversarial attacks. Brilliant, it works. So in this example that I showed, when we add this model, which adds we take into account also the gradient of the original input data, and take that into account, voila, we have the match. The blue and red curves coincide. The improvement is not great, so the network doesn't think that it can improve so much, which is unfortunately the case. So that original red curve was just delusion. It was thinking too much about itself. So we have this cool technique we've been developing, which can turn basically any neural network predictive model into actions. We can apply that everywhere, right? It's artificial general intelligence. We can learn whatever process and then optimize it. So let's apply it to material sciences. I have physics background. I started studying here in Otaniemi technical physics way back, but I have not that much background in material sciences. So this is maybe more based on my youth experiments with chemicals and like put stuff together and see what comes out. Maybe that's not quite the case how material sciences work, but let's pretend. So we know something we want to get out. Then we have some fancy recipe. We put something together, boil it all and cook it and whatnot, pressure and steam and all kinds of funny pressure chambers. And then we measure what came out. Okay, if we're not happy, then we tinker around and do something funny. Okay, this is not how you actually do it. Maybe this was the alchemist's way of doing it way back. I mean, I see some nodding. Maybe there's something like that. At least I think that you have these inner loops where you're trying to make things faster. So it's not just blind trial and error, but you actually maybe have simulations going on. They may be slow to run, but it's still faster maybe than cooking this stuff. So what if we could predict what's the outcome of the simulation and the real experiment? So that's basically it. We just now rather than having an engineer or scientist, material scientist trying to figure out the prediction, we can use machine learning to learn the predictions. But alone that won't help. Remember, if you try this blindly, then you're going to just run into adversarial examples. It's an adversarial attack. So we also learn the uncertainty of your predictions, and then you are good. Brilliant. There's another thing. Maybe you've heard about AlphaZero. It's not always trivial to figure out how to change your recipe. So there's also something where, if you have good predictive models, you can also try to learn how to efficiently search through this very complex space of how to cook things together. But I think those three things, at least, if you're trying to build a material, I think those things are something that are now available in Christmas sales or something. I hope that was useful. Thank you.
So when you spoke about the humanoid robot walking, right, and the model-based
Yes.
reinforcement learning for that, walking is quite a complicated process,
Sure.
if you think about it. And then, so what sort of a model do you use to model that in the model-based reinforcement learning?
Just sequence-to-sequence models, deep neural networks, recurrent deep neural networks. The nice thing about this is that we can model almost everything with a state machine. You know, there's a state of the world, then there's dynamics, and then there's the next state of the world. That's basically the recipe for the whole universe, right? So these things are tremendously general. They can model almost everything. But of course, if you have very nice predictive models, and I'm sure that many of you have been already working with some predictive models, then maybe you can just plug and play. You can add these models of the uncertainty. So you can talk to us. We would be happy checking out whether we can make an AI materials designer assistant or something like that. Yeah.
So yes, I understand that one can sort of learn that from data, but then you would have to see infinite or close to infinite amount of situations where you need to walk. So it still doesn't solve the problem, right?
Well, not really. I think that oftentimes the underlying model for the dynamics is far simpler, like enormously simpler than the recipes. Like if you want to do this, what to do. If you want to do that, what to do. So you can have very simple rules of the game, dynamics, but still how to optimize is very complicated task. So think of playing the game of Go, for instance. It's very simple to find the rules of the game, but not very non-trivial to optimize it. Now this method applies to basically everything. That's the beauty of it. That's also the weakness. You probably have to add a lot of domain knowledge to make it efficient. But I mean, that's why you're here, right?
Yeah, maybe one question on the denoising. So the example that you had that looked like kind of a white noise on the data, and I was kind of wondering, you can have the case that you have a systematic error in your calculations from whatever source. So could you train with a statistical errors and then correct for a systematic error?
If you know the ground truth, I think yes. It's not probably for the same purpose as what we were doing. So we were applying white noise just in order to generate a learning problem whose solution is the gradient that we are looking for. If you have a different problem, sure. I know these similar techniques have been applied for image restoration, for instance. Timo might know more about that. In NVIDIA and other places, they've been doing that kind of stuff. So if you know something about the problem at hand, then you can do more. But you typically need samples then.
Mm-hmm. Okay.
Yeah, I guess the next speaker is ready for presentation, so the floor is yours.